Hello, everybody. We are going now to start the discussion on the conservation of energy equation. And as we mentioned before, it can be written in forms of Newton's law, which is sigma force equals ma, or we can write it as in form of the linear momentum equation or conservation of momentum, which is another form of the same equation. So by the way, in the textbook, the equations are derived in more than one way. So the textbook is giving the equation and different ways of doing the derivation based on different mathematical methods or different basic equations. So I'm not going to go through all these methods. I'm just picking one, and the reason, and I'm making this clear now, that my goal of this video and the next one is not to go through the details of the derivation, because it's already in the textbook and you can go through this yourself. But my goal is to highlight the main points that we go through when we start from the basic equation until we reach the final equation that we're going to use, and the conditions that the final equation would be valid for, because we are going to use an equation that is valid for some special conditions. So it's not valid for all the cases. So you need to understand why we use this equation for these cases, and of course it's important to know how we go from here to there. But the details of this derivation are in the textbook, and I'm not going to go through them in details. And because there are a lot of math in there, so I don't want to waste my time and your time in something that is I think it's easy to understand from reading the textbook. Anyway, so the equation that we can start with is what we derived in chapter 6, which is the linear momentum equation, which is the sigma f is the sum of these two terms. The first term is the accumulation of momentum. The second term is, as we did in the continuity equation, it's the momentum out minus momentum in, which is the same thing that we did in the continuity equation for u dot n, and we said that this will be positive or negative whether the momentum is in or out. So it's the same thing here. I mean, the mass was in or out, so it's the same for momentum. Anyway, so the same thing we did a couple of times before. We don't like to have volume integral with area integral, so we can use the convergence theorem to convert this area integral into volume integral, and then we have two volume integrals added to each other, so we can have them as one integral, which is the summation of these two terms. Now, this right-hand side of the equation is done. We almost reached the form that we want to have for the right-hand side, as only one integral. For the left-hand side, we have the summation of forces. We discussed this before in chapter 6, and we said that the summation of forces can be one of two types, or the forces acting on a control volume can be one of two types. Either the body forces, which are the forces acting on the entire body, and in this case we care about only we care about gravity, which is the gravitational force. For the other type is the surface forces, which are the forces acting on the outer surface, or the surface of the control volume, and these include the pressure and the viscous forces. And now we want to find expressions for both, as we did before, but in this case we want to have general expressions valid for a control volume or a differential volume, not like a general equation or an algebraic equation for the whole system. So we need to remember that the body forces act on the whole body, so it's going to be volume integral or derivative, and the surface forces will be acting on the surface, so they're going to be area derivatives. So this is something you need to keep in mind. So for the body forces, as we said, we are going only to include the gravity, and in this case the differential body force is the differential gravitational force, which is rho g dv. So this is the differential. We're doing this on a differential volume, which is this very small volume here. And now for the gravity, always the gravity always acts in the or towards the ground. Okay, so if we this is the gravitational force, so it's a vector, so it's acting downward. So if we consider that the z coordinate is the vertical coordinate and xy are the horizontal plane, then it's going to be acting in the negative z direction, so it's negative gk. Okay, so the total forces acting, the total body forces is the integral of the differential body force over the whole control volume. And if the density is constant, we can take the density. I mean, well, whether it's constant or not, we'll just put it like this. It's the integral of rho g dv over the control volume. Now we can move to the second type of force, which is the surface forces. So it's the surface forces can be normal forces or can be tangential forces, meaning that the force can be perpendicular to the surface. And for instance, if we have this surface that is the direction of the, or the vector, the area vector is the normal vector to the surface, which is n vector, and it's in the xy plane, so n is in the z direction. And for the same surface, there can be two types of forces. There can be a force that is normal, which is in the same direction as the normal vector, which is in the z direction, and the force can be tangential, either in y direction or in x direction. And the forces are vectors, of course. So we need to define a new term, which is the stress. And we know the stress is the force over the area, or the force per unit area. But here we have if we just define it as force by the unit area, we are missing an important information, which is the direction of force. Meaning that if I have the same force here and the same force here acting on the same area, and they have the same, I mean this force and this force have the same magnitude, then we will have the same value of the stress. But we don't know that it's normal force or it's a tangential force. So we need the stress to take into account three pieces of information: the magnitude of the force, the direction of the force, and the direction of the area on which the force is acting on. Let me say this again. So we need the stress to be fully defined and to take all the parameters into account. That this stress must take into account the magnitude of the force, the direction of the force, and the direction of the area on which the force is acting on, to differentiate between the force, the normal force and the tangential force. So that's why we have this stress is defined as, we give it a symbol sigma, and it has two letters here. So when it has letter z, it means that it's acting, the first letter represents the normal vector to the area, so it's acting on an area with a normal vector in z direction, and the force itself is in the z direction. So if the two letters are the same, then the force is in the direction perpendicular to the area, then it's a normal force. Okay, and there is the shear stress. We give it the letter sigma z, zy. So this z is the normal vector, so the area has a normal vector in z direction, and y is the direction of the force. In this case, the force is parallel to the surface. It can be the same for zx if it's parallel in the x direction. So now, since this this parameter, the shear, the normal and shear stresses have three pieces of information, it's not a vector. It's a new term that's called a tensor. So just to simply clarify this, a tensor is a quantity that accounts for these three information that we just mentioned. So we have three levels or three types of quantities with three levels of information that are provided by each one of them. So the simplest is the scalar quantity. It's like the mass, like the volume. It has a magnitude, and it doesn't have a direction. It's just a magnitude. And then we have the vector. It has the magnitude and direction, and it's defined by three components. So we define it by a component in x direction, in y direction, and in z direction if it's Cartesian coordinates. And then we have the tensor, which has a magnitude, direction, and the plane it's acting on. So it has 9 components. And the 9 components because we have 3 components in each coordinate. So if we have this control volume that we have here, it's like a cube in shape. It has dimensions of dx, dy, and dz. Then we have a surface dx, dy. We have a surface dx, dz. We have a surface dx, dy. For each one of them, we have a normal force and 2 tangential forces, one parallel, in this case, one parallel to y and one parallel, one in y direction, one in x direction. Here we have one in z direction or z direction, one in y direction, and the same here. So each one of these red dots represents a surface, center of each one of the surface, and the 3 components, as we see, per surface. So we'll have 9 components, and of course we have other the same on the other 3 faces of the cube that we don't see here. So we can define this stress tensor as sigma ij, which is sigma xx, sigma xy, sigma xz, and the same for y and z. So it's now a vector, a matrix of 9 components. And let's recall that the stress can be one of 2 types: a normal stress, which is the pressure, and the shear stress, which is or the viscous stress, which is the tangential or parallel to the surface. So we can write the sigma as a pressure vector, which is x, 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 y, y, z, z, which is only the diagonal, and the shear stresses, which is the viscous forces. And now we can express the total forces as sigma ij, and now sigma ij takes into account everything, the normal and the shear. So this is the normal and shear. This is the total surface stresses. So we have the sigma dot n dA, and we like to keep everything as a volume integral, so we can use the divergence theorem, and we can add the body forces to the surface forces, and now this is the expression of the total forces we have on the control volume. Now we can take this and go back to the linear momentum equation and plug this term in the left hand side of the equation, and now we have volume integral. We can take everything in one side, so we have everything equal to 0. We can get the derivative of this. Derivative of 0 is 0. This means that whatever is inside these brackets is also 0. It's simply what we did in the continuity equation before. And now we can have this equation written in this way. This is a very famous equation. It's called Couchy's equation. It's valid for any type of flow, compressible, incompressible flow, for steady and unsteady flow. It's valid for Newtonian, non-Newtonian flow. It's valid for anything. We can also write Couchy's equation in a more simpler form, and this just with some mathematical manipulations. We will expand this and expand this term, and then we can rewrite the equation. It's just math. It's the derivative of the first by the second, and the derivative of the second by the first, and then we can rearrange the equation, and then we'll find that whatever we have here in this equation, in this bracket, is the continuity equation, which is equal to 0. So the equation can be written in a simpler form, like this, and which will have 3 components, and we can write this as the 3 components of Couchy's equation. This is the total derivative that we discussed in two videos, or I don't remember the previous, or the one before the previous, the video before the previous. And that's all. So it includes the stresses, normal and shear stresses. It includes the gravity. So this is the total forces acting on the body, and this is the can be taken as the summation of forces acting on the body. So anyways, this is what we are going to stop here now, after this long derivation, and next time we will see how to deal with this equation, because it's a very important point, because from here we can know how we will reach the last or the final equation that we are going to use later, inshallah. So I'll stop here and we'll continue next time, inshallah. See you then.